So we're on our next topic in this course, which is conic sections. So this section actually doesn't have any homework. It's just kind of a visualization of what we're doing and why it's called a conic section. So notice in front of you, you have those cones there, a cone sitting on top of the other cone. Anyways, you can get these shapes, the parabola, the hyperbola, a circle, and an ellipse, by making a slice through that cone with a plane. I just want you to be aware those colors, it kind of shows the area. When we're looking for those, we're not finding the area, we're just kind of finding the perimeter of those shapes. And so in this next picture, you can kind of see what you're getting as you cut through the conic. You kind of section it off the shape that you would get. And so we've already dealt with circles before, and we've dealt with parabolas that face up and down. So in this section, when we go into parabolas, we're going to give the form of the equation, and we'll also deal with parabolas that face left and right. So I am going to jump into ellipses before parabolas, since we've already talked about parabolas in the past. Ellipses and hyperbolas, the equations are really, really similar. And I think that those go really well together. So the first shape that we're going to look at is the ellipse. So let me kind of read through the definition, and then we'll talk about how they get this definition. And then we'll talk about terminology that will help us with graphing these. So by definition, it says that an ellipse, let's make sure that we can do this. So an ellipse is a set of all points in the plane that the sum of whose distance from two fixed points, which is called the foci, is constant. Okay, so really what is that saying? So this image that I pulled over here kind of explains this. So basically we have 2 points in this plane. These, each one is called a focus. Plural for focus is foci. And so basically think of it as maybe you have 2 tacks and a loose string, and that loose string, each end of the string is tacked on here. And then we pull that taut, and as we pull it taut, we can move it around in an elliptical shape. And so basically, this right here, think of that as the string. And as we move this around, it's going to give us the shape of the ellipse. And so it says the sum of those distance is the same length. It's the same constant. So no matter where we pull that string, d sub 1 plus d sub 2 is going to be equal to the same value. Okay, that is not going to help me so much with graphing these, but that is the definition of an ellipse. So just so that you have it. But now let's go through and let's look at the standard form of ellipse. This is what's going to help us graph things. So the standard form of an ellipse, notice that it's almost looking like a circle, where we have, remember, a circle is x minus h quantity squared plus y minus k quantity squared equals r squared. And this in here, we have some a squared in the denominator. We have a b squared in the denominator. And instead of equaling to r squared, we have equals to 1. So in the standard form, we can see a lot about what's going on with this ellipse. When it's in this form, we can tell what the center is right away. Just like with a circle, it was the opposite signs inside that parentheses quantity squared. That was the shifting, the opposite of than what you would think when we did transformations of graph. And so the center of the ellipse is always going to be at HK. H is always with our x value. and K always with a Y value. So depending on, is my ellipse elongated towards the x-axis, or is it elongated with the y-axis? Depends on this value in our denominator. And here, if our major axis is parallel with the x-axis, then the number underneath the denominator is bigger. So A is bigger than B. So notice that A value is underneath the X. That's how I remember which one it is. The larger number, if it's underneath the X, it's going to be elongated with the X-axis. If the larger number in the denominator is underneath the Y term, then it's elongated with the Y-axis. This major axis that I just was talking about, that is the longer of the two that go through the center. So here our major axis, notice, is parallel to that x-axis. And over here, our major axis is parallel with a y-axis. So you're looking at the which one is larger and in the denominator. Okay, so I usually always have A, the larger number. In this book, I think that they do it a little differently than what I'm used to. So the major axis, that length, depends on, you're looking at the larger axis. So the major axis length, when it's parallel to the x-axis, this is equal to 2 times A. So notice over here, we have one that is a length A here. So A plus another length of an A here gives us that 2A. So our major axis parallel to the y-axis, notice that I have a B value here and a B value here. So whatever that bigger number is underneath in the denominator is going to tell us which way it's parallel to, which way it's elongated to. And in this case, the major axis length is 2B. So notice there's two axes that go through this center. That major one that we just talked about, but there's also the smaller length. And so this smaller length in here is called the minor axis. And that minor axis has a length of 2B. And in this case, where our minor axis, in this case, is 2A. Okay. So depending on, it's always on the major axis, is our foci. So these 2 points are always going to lie on the major axis. It's always going to be inside the ellipse. And those are called the foci. So for instance, we might have a foci right here and a foci right here. And to find those foci depends. Are we changing it with, notice, to get from the center to this foci, I'm changing the value of X. I'm either going to the left or I'm going to the right, and that affects my value of my point. Where over here, my point on my X, where over here, the foci on this major axis, I'm either going to go up to get to the foci from the center or I'm going to go down. So that's affecting the Y value of my point. So to get that value, we're going to either add or subtract a length of C from our center. In this case, it's going to be from the X value of the center, or add and subtract C from the center, and this is going to affect my Y value. So to get C, it's always equal to the square root of A squared minus B squared. It's always the largest number underneath the denominator once it's in standard form, minus the smaller number squared. Those squared and then take the difference. So for instance, in this case, to get the foci, let's just see. So to get the foci here, this is going to be remember my center is at HK, so it's going to be H minus C, and let's just do H plus or minus C, comma, K. So the Y value is staying the same, but my X value is changing either left or right C units from the center. Where in this case, I can find my foci by either adding C or subtracting C from the Y value. So the foci are going to occur at H comma K plus or minus C. So pretty much the same thing to get what are called these vertices on these ellipses. So the vertices on our ellipse occur either at the endpoint of our major axis or minor axis, depending. Well, actually, always. So these are vertices of the ellipse. Same thing, right here, right here, right here, right here. Those are all vertices on the ellipse. So notice, if we know what our center is, we can easily find out what the vertices are. So going back to our equation, notice we can get our length of A by taking the square root of our denominator here. And we can get the length of B by taking the square root of the denominator there. It has to be in standard form though. So let me just go a little further. So these vertices, when we're on the major axis, when it's parallel, major axis is parallel to the x-axis, is going to be, it's affecting the x value of my point. So from my center H, I'm going to subtract A, or I'm going to add A. So it's going to be H plus or minus A, comma K. If I'm on the vertice of my minor axis, let me just do it up here. In this case, I would be going up or down that value of B. So going up or down affects the Y value of the point. So X stays the same, and I'd have K plus or minus B here. Okay, so vertices, major axis. When it's elongated with the y-axis, vertices on the major axis here, notice again, it's affecting the y value. So it's going to be H comma K. The bigger value is B, so K plus or minus B. And the vertices on the minor axis, So I'm going to the left or to the right B. So that's affecting my X value, H plus or minus A, comma, K. So as long really as we know what the center is, we know the length of our major axis and minor axis, we can get a picture of this ellipse really well. Sometimes we're not given the equation though, we're given information about the ellipse, and so we kind of have to go backwards and figure out what the equation is. So I'm gonna pull up some examples. Let me just see if there's anything on here that we didn't touch. So just kind of reading what this says, it says for both types of ellipses, the center is HK and the vertices are the endpoints of the major axis. I also said the minor axis. So on an exam, I would ask you probably, what are the vertices of this ellipse on the major and the minor axes? The value of C is found to find the coordinates of each foci. And the foci are located on the major axis and are each C units away from the center. So that's always the case. So recall, we had a center or a circle before, and when it was in the standard form, just flip this up for a second. X minus h quantity squared plus y minus k quantity squared equals r squared. So technically, when we're looking at these conic sections, it might not be in standard form, and we should be able to identify by looking at the equation, is this going to be a circle? Is this going to be an ellipse? Is this going to be a hyperbola or a parabola? In order to tell that it's an ellipse versus a circle, the coefficients when we have something in the form of, let's say, ax squared plus cx. So how about bx plus c? And then we're going to have something in the form of dy squared plus ey plus f equals 0. If the numbers in front of, this is what we're looking at to tell which shape it's going to be. If the numbers in front of the squares are the exact same number, it's a circle. So if A is equal to D, then the conic section is a circle. Is a graph of a circle. If they're not equal to each other, so if A does not equal D, then it depends. If they're the same signs, so if A and D are both positive or negative, so the same sign, but they're not the same number, then it's an ellipse. And we'll also find out where A doesn't equal D, but opposite signs. So one's positive, one's negative. Then we can tell that it's going to be a hyperbola. If we don't have an x squared, we only have an x squared, or we only have a y squared, we don't have both squares in there, then I know it's going to be a parabola. So in front of us, we have an ellipse in standard form, x plus 4 quantity squared over 9 plus y plus 2 quantity squared over 4 is equal to 1. So it's in the standard form. I don't have to manipulate it to look like this. I notice that the larger number is underneath the x terms. So this tells me which direction that this is going to be elongated. So because the bigger number is under x, it's elongated with the x-axis. So it's going to look like this shape. So remember, this was in the form of a squared over b squared. And so I can tell what my a value is. Well, a squared is 9. So I know that, and a is a distance. So when I take the square root, I'm ignoring the plus or minus. I'm just looking at the plus or minus square root of 9. I'm sorry, just the plus square root of 9, which is 3. So I know a is 3. My b value, b squared is 4. So I know that b square root of that is 2. And it's also a distance. In here, I can tell what h and k are. This is in the form of x minus h, so always opposite sign. So my h value over here is -4, and my k value is -2. So we know we have a center at -4, -2. So from this piece, we know how to graph this. So we're just going to graph our center, and then we're either going to go left or right. In this case, the bigger number, A. And then we're going to go from the center up or down 2. So we're going to now look at plotting this point of our center, which was -4. So going over to the left 4. And down 2, we have our center. So this is telling me it's elongated. This helps me knowing which way it's elongated. So I'm going to go over 3 units to the left and to the right. So if I go over 3 units to the right, notice I already know what that point is. -4 plus 3. So that would be, so I have vertices at -1, -2. And if I go over in the other direction, 3 units, so to the left 3 units, subtract 3 from -4, I get to -7. So I would have -7, -2. Now I want to get the vertices of my minor axis. And so that's affecting my y value. So I'm either going to go up 2 from the center. So if I go up 2 from -2, my y value is going to be 0. X stays the same. So -4 is 0. And if I go down 2 from -2, I have a point at -4, -2. So now I have these points. I know what my ellipse looks like. So that's not a perfect shaped ellipse, but that's an ellipse. So I made a little mistake here. When I went down 2 units from -2, that should have been -4 and -4 on our minor axis. So really finding C to me doesn't help me. And I really don't, it doesn't help me with graphing it. Sometimes those are important points, these foci, but for graphing, it doesn't really help me. So I'm not worried about finding those. If we did want to find those though, because maybe your homework asks you to do that, recall C is equal to the square root. The larger number in this case is a squared, so 9 minus b squared, which was 4. So C here is equal to the square root of 5. Square root of 5 is about 2 point something. So technically you're going left and right on the major axis, root 5. So I'm just going to write that left or right. So I have -4 minus root 5. Y value is the same, -2. Or, because the major axis is parallel to the x, it's -4 plus root 5, comma -2. So the next example is not in standard form, and we have to put it in standard form so that we can see what the shape of this ellipse is. I know that it's an ellipse by just looking at the standard form, noticing the coefficient in front of my x squared is 1, it's not shown, and my coefficient in front of the y squared is 9. These are not the same number, so it's not a circle. They are the same sign, they're both positive in front, so that tells me that it's an ellipse. We'll keep on saying this, so hopefully that you'll get that as we go through and talk about, we haven't even talked about hyperbolas yet or the others. So notice that when we had it in standard form, we had perfect squares. So remember, we've been completing the square in this class. That's exactly what we're going to want to do here. So we want to group our x terms together, we want to group our y terms together, and we want to get the constant on the other side of the equation. So let's go ahead and rewrite this doing that. And so doing that, we have x squared plus 6x. So I'm going to leave a spot here because I want to add something to this to make it a perfect square. And I'll figure out what that is in a second. Plus 9y squared minus 18y is equal to -9, because I have to subtract 9 on both sides to get that constant to the other side, plus whatever I added on the left-hand side. Whenever I add on one side, I have to add on the other. So looking at what is the same number, I would add to get 6. So half that number, that would be 3. 3 plus 3 is 6. I'm going to take that same number, 3, and square it. So 3 squared is 9. That tells me I'm going to add 9 to both sides to make this a perfect square. Unfortunately, I can't complete the square yet on my 9, on my y terms, because of that 9 in front of the y squared. So let's first rewrite this x squared plus 6x plus 9 as a perfect square. So the same number that we multiply to get 9 and add to get 6 was 3. So this could be rewritten as x plus 3 quantity squared. Recall, in order to complete the square, that coefficient in front of the square had to be 1. Before in the past, when we were dealing with circles, we could divide every term by that number. But if I did that, that would make a coefficient in front of my x squared not 1 anymore. So I need to go and manipulate this. So how we manipulate that is we're going to factor that coefficient of 9 out of both of the y terms. So if I pull out a positive 9 from my y terms, I'm left with y squared minus 2y. And I'm going to want to add something in here to make this a perfect square. Think about it as we're adding 0 inside this parentheses. So if I add something on this side, I'm going to also have to subtract it to make it 0. This is equal to -9 plus 9, which is 0. So figure out what is the same number that you would add to get -2. So half that number, which is -1. And so we're going to take that number, -1, and square it. So -1 times -1 is 1. And I'm also going to subtract 1 in here. So this was like I'm adding 0 inside my parentheses. And this right here is a perfect square. So I technically don't want that -1 inside that parentheses. And so I can move it outside the parentheses by multiplying it by the coefficient and pulling it out. So let's just rewrite this. This is x plus 3, bringing down my x plus 3 quantity squared, plus 9 What's left inside this parentheses is now a perfect square. So that's y minus 1 quantity squared. But I multiplied 9 times -1 and I pulled it outside of the parentheses. So this would be a -9 outside the parentheses equals 0. So I'm almost there. I want to isolate my perfect squares. I don't want that constant of -9 on that side, so I could add 9 to both sides of my equation. And if I did so, I would get x plus 3 quantity squared plus 9 times y minus 1 quantity squared is equal to 9. This is not quite in standard form for the ellipse. If you look back at that formula sheet, that was set equal to 1, and the coefficients in the numerator in front of those quantities squared was 1. So we want to set this whole thing equal to 1, and we can do so by dividing each piece in our equation by this 9. So if we do so, we now have x plus 3 quantity squared over 9 plus y minus 1 quantity squared. So our 9's cancel. Just so you help see it, I'm just going to write a 1 down there, is equal to 1. Okay, so we're now in the standard form of an ellipse. And so through here, we should be able to figure out what the center is. We should figure out, is it elongated with the x-axis or the y-axis? We can find the vertices on the major axis and the minor axis. And we could find the foci if we wanted. So looking at this HK, H is always with the X, K is always with the Y, opposite signs. So it's going to be center is -3, +1. I'm looking at which one is the larger number in the denominator, 9 or 1. So I notice 9 is the larger. 9's underneath the X term, so that tells me it's elongated again. This example is elongated with the major axis is parallel to the x-axis. So we have this sort of shape. So I have a squared is 9. So again, my a value is the square root of that, which is 3. My b value, b squared is 1. Take the square root of that, b is 1. Okay, so let's plot our center, -3, 1. So go to the left 3, up 1. Elongated again with the x-axis. So from there, I want to go left and right 3 units. So if I go to the left 3 units from -3, that's -4, -5, -6. So this one vertex on my major axis is -6, 1. If I added 3 from -3, my x value is now at 0. So I have another vertex at 0, 1. And then I want to go up and down 1 unit from my center to get my points on my minor vertices. So if I go up 1 from 1, that gets me a y value of 2. And if I go down 1 from 1, that gets me a y value of 0. X stays the same. So I'd have -3, +2, and -3, 0. And so from there, joining our major minor vertices and graphing this, we get the following shape. So a lot of what we're doing to get these in standard form is using that practice of completing the square. So I don't know if you remember at the beginning of the semester, I said, you got to get this down. We're going to be using completing the square over and over and over again. And here is a main reason why I stated that. So if we wanted to find the foci, we could. For ellipse, it's different for a hyperbola, but very similar. For ellipse, c is equal to the larger number. In this case, it's 9, a squared, minus the smaller one, which is 1. So c is going to be the square root of 8, which if I wanted to reduce that, pulling out the perfect square, this would be 2 root 2. So because I'm on my major axis is parallel to the x-axis, I would go to the left and right root 8 from the center. And so left and right is affecting my x value. So I'd have, my center was -3. So I would subtract 2 root 2. Y is the same 1. Or -3 plus 2 root 2, comma 1. So here's an example where we're given information about the ellipse and we want to find the equation. So we're given that the foci occur at 5, 1 and -1, 1, and we're given that the major axis has a length 8. So when you're given information, I think it's really helpful to start by plotting your points and kind of decide, is this elongated with the x-axis or elongated with the y-axis? Because that's going to help us with getting this in the standard form. So if I plotted my points, 5, 1 and -1, 1. So going over to the right 5, up 1, I have 1 foci. And if I go to the left 1, up 1, I have another foci. So in order to find this equation, I know foci are always elongated are on the major axis. So this is going to be elongated with the x-axis. And so I have x minus h quantity squared over a squared plus y minus k quantity squared over b squared. This is just the standard form, equals 1. So remember the center, we got the foci by looking at the center and going over left C and right C. So I know if I can find the midpoint of these 2 points is the center of the ellipse. So recall, we looked at midpoints, finding midpoints of 2 points. Recall you add your x values together. So here I would have 5 plus a -1. And then we divided that number by 2. That would be the x value of the midpoint. To find the y value of the midpoint, we're adding our y values together, 1 plus 1, and we divide it by 2. So simplifying this, I have 5 minus 1 is 4. 4 divided by 2 is 2. And the y value of the center, I have 1 plus 1, which is 2. 2 divided by 2 is 1. So I know my h value in here is 2, and my k value in here is 1. So I now have these values in here. So I know what h and k are. The other thing that I know is my major axis. My major axis has length 8. So remember, we go over A one way and over A the other way. So I know that 2 times A, we talked about the major axis being that length, is 8. So I know what my A value is. My A value, well, 8 divided by 2 is 4. But I want A squared, so I can look at A squared is 16. So let's go through and plot what we have so far. So we have x minus h, so x minus 2, quantity squared, all over a squared. Well, our a squared was 16 plus y minus k, but k was 1. Quantity squared all over b squared. I don't know what b squared is. Equals 1. So I need to figure out what b squared is. So if we don't have a value, one way that we can find that is if you're given a point on the ellipse. I'm not given a point on the ellipse, but I can find that point on the ellipse because I know my center, again, is 2, 1. So let's just plot that real quick, 2, 1. But I also know that if I add, because my a value is 4. So if I add 4 from 2, that would get me up to 6. So I know one of my points on this ellipse is 6, 1. So if we know one point, we know what x is, and we know what y is for one point. So I know when x is 6, my y value has to be 1. So if we go in and we plug in that point for x and y in this equation, then we're going to have an equation just with one variable left, and we can solve for what b is. So let's go ahead and do that. So we have 6 minus our 2, quantity squared, all over 16, plus y, which is 1, minus 1, quantity squared. Oops, that's going to give us that's going to give us that's not going to work there. Because that's going to give me 0 where my b is. So let's look at the other point and let's see if that would work. Actually, that's going to give me a 0 there. Okay. What I'm just doing right now, when I'm plugging in that point, I'm always going to get a 0 over b squared. So that's not going to help me. Okay, let's go a different route. We're always going to have enough information to find it. That might work sometimes, but it didn't work our time. So let's go back. Let's look at something else we know. We know that C is equal to the square root of a squared minus b squared. Well, I know what C is. C is the length from a foci to the center. So if I was going from my center of 2, and I would go over to the left 3, and I would go to the right 3. So I can see that my C value is 3. So I have 3 is equal to the square root. My A value we found was 4, so 4 squared minus b squared. And we want to find out what b is. So I have 3 is equal to the square root of 16 minus b squared. Okay, kind of going back to the beginning of the semester, solving these different types of equations. And so I know how to solve an equation with a radical. I would isolate it, it's already done. We can raise both sides by the index of the radical in this case, square both sides to get rid of the radical. So I get 9 is equal to 16 minus b squared. Let's get b squared by itself. Let's subtract 16. So 9 minus 16 is negative 7 equals negative b squared. Divide through by negative 1, I get b squared is 7. Technically, notice I only need to know what b squared is. I can figure out what b is, take the square root of both sides, and I know from my center I'd go up and down that value to get the graph. But my b value, b squared is 7. So now I have my equation of my ellipse given the information about it. So I have x minus 2 quantity squared all over 16, y minus 1 quantity squared all over b squared, which is 7, equals 1. So given the information about the ellipse, we are able to find the equation of the ellipse.